start whenever. Okay. Good morning, everyone. My name is Andrew Butte. I am the group leader for Group 1 refrigeration cycle experiment for next week. So some theoretical background around refrigeration cycle. There's 4 main steps in the cycle. Those steps being compression, condensation, or heat rejection step, expansion, and then evaporation. Refrigeration cycles are used in many modern cooling systems to refrigerate things, so in your supermarkets, but they're also used in industrial systems to help cool systems, and it essentially works as the reverse of the power cycle. Because in a power cycle, you are trying to get work out, and in a refrigeration cycle, you are basically trying to pull heat out. So an important theoretical clarification that needs to be made for this experiment is the difference between an ideal cycle and a real cycle. An ideal cycle assumes perfect expansion and compression and no losses, versus a real cycle, there are pressure drops due to fluid flows, and there's also irreversibilities in the heat transfer to and from the surroundings. You can see here on the right, I have 2 figures showing the PV diagrams for an ideal refrigeration cycle and a real refrigeration cycle. Important to note is the difference between step 3 and 4 in the top, and 4, 5, and 6 that you can see. They're not perfectly isentropic as the ideal cycle assumes. So some important diagrams for a refrigeration cycle include a PV diagram showing the pressure volume change, the temperature enthalpy diagram showing the temperature and enthalpy through the steps, and a pH diagram which helps to compare the performance of different refrigeration cycles compared to one another. So as I mentioned, there are 4 main steps. From steps 1 to 2 there, you have adiabatic compression. From 2 to 3, you have heat rejection. 3 to 4, you have isentropic expansion, and 4 to 1, you have exhaust. So the experimental apparatus that we will be using for this experiment is the TRCVC computer-controlled vapor compression refrigeration unit. As I mentioned before, it has all the major components that are necessary for a refrigeration cycle, including a condenser, an evaporator, a compressor, and this one also has a heat exchanger. So some of the main components to focus on for this system include the condenser, the evaporator, the compressor, a water reservoir, as well as an expansion valve. The expansion valve is particularly important in a refrigeration cycle because it removes pressure from the system and allows for the phase change of liquid to vapor, which is associated with a refrigeration cycle. So the procedure for this experiment, there will be 2 main exercises that are conducted. The first exercise will focus on determining the inlet power, produced heat, and coefficient of performance for the system. It'll start by turning on the system, turning on the AB-1 and AB-2 switches, and setting the flow rate to 5 liters per minute. Once the compressor is turned on, we will set an approximate value of 40%. We will allow the system to become stable and report all necessary data and values in the provided data table shown here on the right for exercise 1. For exercise 2, we will gather information to construct a pressure enthalpy diagram for the ideal cycle and use it to compare the real cycle that we're using, or that we are using during this experiment, to an ideal cycle. It'll start similarly by turning on the software, turning on the AB-1 and AB-2 switches, which will turn on the evaporator and compressor. Again, the compressor value will be set to 40. We'll adjust the evaporator side heat exchanger flow rate 3 different times, as 3 different trials will be run in this experiment. One at 6 liters per minute, 4.5 liters per minute, and 3 liters per minute. Once the system has become stable, we will again record the data in the provided tables. Data will be collected according to the table provided, and will be collected to draw necessary curves, determine the coefficient of performance of the refrigeration cycle, and collected to determine the heat generation in the condenser. So the data analysis performed will be determining the coefficient of performance for the refrigeration cycle, calculating the heat generated for the condenser, the electric power of the system, and finally the data that we collect will be used to draw a pressure enthalpy curve for the system. So the equations that I've found for these in the book include the coefficient of performance, which is the heat generated for the evaporator over the work of the system. And also important to note is the electric power of the system, which is given by the heat times the mass flow rate. So the expected results for values such as the coefficient of performance for this cycle are, again, using the equation that I outlined before in the previous slide. A sample case was found in the book, which is somewhat similar to the refrigeration cycle that we will use. As you see, it uses working fluid R-134A and has set conditions for the evaporator and condenser temperatures. Using this, I performed a set of sample calculations using the R-134A saturation tables to determine pressure and enthalpy and the entropy of different stages of the system. And using this, there was a final coefficient of performance found to be 3.064 for this cycle, which again is somewhat similar to the cycle that we will be using in our experiment. There's my references. Are there any questions?